Before we continue on with actual discussion about dinosaurs, we need to take a little side jaunt into the topic of geologic time. Usually whenever you see or hear about a new dinosaur, or somehow dinosaurs appear in the news, a couple of things that they'll say will be how old it is, or they'll say it comes from the Jurassic or the Cretaceous or some other time term like that. And that's the whole subject of geochronology or telling geologic time. And geologists have a very particular way or set of methods of doing it. If you look at that picture right there, you see a bunch of students with me, and we're collecting rocks, doing what we do, and we're in southeastern Nebraska doing that. And for a lot of people, it's hard for them to say, okay, you've got a rock. How does that say anything to you about time or age? Well, let's talk about that. So the first thing to think is that there is a principle called superposition, and this is saying that if you see a stack of sedimentary rocks, and sedimentary rocks are those rocks that are laid down bed by bed, you can see the layers in this cliff in Colorado, and they're laid down sequentially so that the bed at the bottom, the rocks at the bottom, are the oldest, and they get progressively younger and younger towards the top. So right there at that one place, you can make some statements about age. You can say that this or that rock, wherever you found it, is older than or younger than any other rock that you find there. So that's not actually putting a numerical age on it, but it's making a very powerful statement about older than, younger than. Now, imagine if, besides looking at these rocks here, let's say you were able to collect fossils in this cliffside. Then you would know that a fossil that you collected, say in the lower half of this cliff, would be older than any fossil you collected in the younger, the higher part of the cliff. Okay? This is the principle of geologic time. It's the very starting point. We use superposition plus fossils, and doing that, we've created the geologic time scale. It's sort of a calendar for rocks on planet Earth. And so if you see any place where rocks are exposed, like the Grand Canyon here, or in the sides of a riverbank, or in a road cut, or just on a mountainside, those rocks, if they're sedimentary rocks and have fossils in them, we can put them on this calendar that we use to date rocks with. How do we get there? We get there from this fellow, William Smith. So look when he was operating a couple centuries ago in England, and he's responsible for a whole bunch of things, but one of them is that wherever he collected fossils, not only did he say, well, I got it here or there in this point, he would look at places like this, certainly not like the Grand Canyon in England, but he would look at how far up and down, say, a canal dig, or a hillside, or a mountainside. In some areas, these things would be, and he would record it. And from that, he recognized that fossils aren't random. They're not just thrown here and there in the rocks. They occur in a very particular order. That is to say, this fossil will, if it occurs in one place before another fossil, as you're going upward from these oldest rocks to the younger, then it usually consistently will do that elsewhere. So in this little diagram right here, I know it's sort of confusing, but imagine a big cliffside sort of standing here off on the left, and each of these letters, A, B, C, D, E, F, for these 6 things, these are different species. These could be 6 different dinosaurs, 6 different fossil petrified trees, whatever. But notice this says that he's found fossil A way down here at the bottom, and as long as there's a vertical line, that means that in the rocks that are sort of the equivalent here, he can find it, but then there's some point where he stops finding it. Then another paleontologist maybe collects here, and when she's doing it, she has a zone where she just has fossil A, but then at some point up here, she starts collecting fossils B and C. And notice again with the vertical stripe, you collect it up vertically, but at some point you reach the last of fossil C. And every fossil species on planet Earth has this situation. You have the oldest or lowest place where you find it, you have the rocks in which it's found, and then you have the last possible occurrence of it. And what William Smith recognized is that this pattern holds regardless of where you're at. You could be in England, the United States, Argentina, Antarctica, anywhere, and the general pattern holds. We call this biostratigraphy. So stratigraphy is the study of strata, or those beds of rock, and bio is the study of the fossils in them. And here you see three different localities. You see the little drawings of rock, sort of this is supposed to be the mountainside here, and in this extreme left one you see that these cute little icons represent the different fossil groups, and you see that this one is found at the bottom. He finds it, and then there's some point where it stops being found. Above that then you have another fossil where it has its first occurrence, you find it, and then the very last, and then here. So notice that fossil A consistently occurs after fossil C has occurred and disappeared, and fossil B is younger than both of them. Now look at these two other locations. The actual distributions might vary a little bit. They might extend up or down one way or the other, but consistently fossil C is the oldest, fossil B is, or fossil A, excuse me, is the middle range fossil, and then fossil C is the youngest. We still do this today. We do this around the globe like these students are doing it here. We collect fossils, we measure and note where on the mountainside or road cut they are found, and then this is collectively aggregated for the entire globe everywhere. And this has created the geologic time scale. It's our geology calendar of life on Earth. It tells us when particular fossils didn't exist, because it's before they came into being. It tells us when we can find them in the rock record and when we stop. This geologic time scale is analogous to a calendar. And I'm not going to go over this bit by bit, did it in class, but again, if you think about a calendar you're used to, you can divide it into from big units like decades, centuries, things like that, all the way down to days and even smaller, minutes, seconds, fractions of a second. We do the same thing in geology with these rocks, but we have different terms, and they're certainly bigger units, eons, eras, periods, etc., etc. And again, you see for both of these, you can use this calendar to mark particular events. In this case, particular killing events. Okay. These names for time terms are based on what fossils are within. So just as you know that January comes earlier in the year than July, and both of those come earlier than December, and therefore anybody born in those respective months, or if anything happens in those respective months, you can say that something is older than or younger than that. We do that with rocks and fossils in rocks. And so when you see terms like Jurassic, Pleistocene, Cretaceous, that's just like we're saying January, July, August, December. The geologic time scale, there it is. There's the entire thing. And again, remember, we start just like we're looking at rocks. The oldest is at the bottom, and it gets younger progressively up. And for this class, what we're going to be worried about is this middle purple area that is called the Mesozoic era. Mesozoic literally translates to middle life era. And then it consists of three shorter units that are called periods. There is the Triassic, the Jurassic, and the Cretaceous period. All of this green part down here below it, that's older. This is the time pre-dinosaur, before dinosaur existed. All of this purple area, this is the Mesozoic, this is the era of the dinosaurs, and then the Mesozoic ends, and everything above that, the yellow rocks, these are rocks that are younger than dinosaur times. So all of these names, these are based upon the fossils we find in them. But what about these numbers over here? There are also numbers that are associated with it. And these numbers are referred to um, millions of years ago. So for instance, we live at the top of this black line right here, 0 years ago, so today. But let's go back to this dinosaur time and say that, oh, the dinosaur time, let's just pick this one here, 200 million years ago, is right smack in the middle of the era of the dinosaurs. But something older, way down here, 416 million years ago, that's before. Well, where do we get those numbers and what are they? Well, we call them, first of all, absolute dates. So a lot of times when you see the news or hear something about a dinosaur is found in China, for instance, and it is 135 million years old. It's a number. How do we get it? Well, we're going to talk about it briefly in this class, but I want to make sure first that you're aware of the difference between what we're talking about. So first of all, relative ages or dates. Those are the things where you're saying that something is older than or younger than something else. So again, for instance, I am probably older than all of you students in the class, and you are all younger than me. We haven't said anything about our actual ages, but we know a pretty important fact about older than, younger than. That's relative age. Absolute age means numerical. Anytime you see a number, that means it is what we call an absolute age. Where do we get that? Well, that comes from radioactive decay of, and I should have underlined it or bolded it here. Let's try to do it now. Bold, underlined. This comes from radioactive decay of igneous rocks. Everything I've talked about so far has been fossils in sedimentary rocks. Well, let's look at this situation. In this situation right here, you see the layering of rocks, and so these are sedimentary rocks. If a geologist or paleontologist came up here, he or she could find fossils in there, which would immediately place these rocks somewhere on that calendar, and therefore those are relative ages. So let's say I found a dinosaur bone in here that told me as a paleontologist that these are Cretaceous age rocks. This particular weird rock that's kind of moving vertically through here, this is an igneous rock. And igneous rocks are things like magma and lava that are so hot that they've been melted. They're liquid. They're super hot. And a lot of times these superheated rocks, they literally will shoot up and cut through. They'll cut across existing sedimentary rocks. Now from these rocks, we can measure the amount of radioactive material in there. And we have a method of dating this, and I'll talk a little bit about it in just a second, that can give us some measure of the date in numerical terms. So, one cliffside, and this part tells us relative time. This part tells us absolute time. But they're not the same age. So if this is Jurassic and this gives us a number, it's not saying that that's this. What it does, it tells us that these igneous rocks have cut across these other ones. So these had to exist first. So this is an igneous rock. It's dated at, let's just do a hypothetical. If I say it's dated at 100 million years old, all that tells us is that these rocks that it is cut across must be older than that date, or this thing must be younger than that one. But here then is the big problem. One set of dates, the absolute dates, come from igneous rocks. They tell us the date that that rock cooled. The other rocks are sedimentary rocks that contain fossils, and they tell us the age in relative terms, in name terms, but we want to put actual numbers on these fossils. So how do we do it? Turns out there's a simple way, simple resolution. The Earth is filled with places like the previous picture that I showed and like this one here, where you have igneous rocks, here this thing that's called a dike, that have cut across existing sedimentary rocks. And so here's a cartoon at the top. Here's some students down here looking at the exact field situation. And so let's say I find a fossil in these sedimentary rocks and then have somebody date in their lab these igneous rocks. I would then automatically know that any number I get from this igneous rock here is going to be a number that's younger than the actual age of these fossils. So let's look at a quick example. Here I've sort of dropped in a cartoon of a dinosaur bone. Let's say a paleontologist has found this dinosaur bone here, and she has then decided she wants to get some estimate of its age in absolute terms. She knows it's Jurassic, but she sends off a sample of this igneous rock to her igneous geology colleague, and he will age date it using his lab equipment at 185 MY, or million years ago. Then she automatically knows from her colleague that her dinosaur bone is greater than or older than 185 million years old. It could be 1 billion years old, it could be 186 million years old. You don't know exactly how there. So what do? As it says at the bottom, repeat, repeat, repeat. We go around the globe and look for situations where you have this happening, or then you have dikes, mini dikes, cutting across in every different way. And so you make a whole bunch of statements that, it is older than 185 million years old, but younger than 190 million years old. Then maybe next year somebody finds a situation that cuts it even finer and finer. And we've been doing this now for a couple of centuries, and that's how we're able to pin numbers on actual fossils as we find them. We kind of mix our igneous studies with our paleontology studies. I'm going to have you do a few simple problems on the test, just so you have a simple idea of how this is done. And you need to use this radioactive decay curve diagram. Notice the y-axis on this side is the proportion or the percentage of parent isotope atoms, and down here is the number of half-lives. The half-life is the time it takes for half of the parent to decay, to go from some radioactive material to a stable material. This is explained more fully in your book, so I refer you to that. But notice on this diagram, if you have 100% parent, that's what happens when an igneous rock is first formed. And then over time, it slowly will decay so that the radioactive material gets less and less, and you get more and more of the stable material, which we call the daughter. And notice at the time where it's 50%, so half parent, half daughter, half radioactive, half not, we call that time its half-life. And we have measured this half-life for many radioactive elements, and we know it. And so we can send a given rock to a particular lab, and they'll have the equipment, and they can measure this percentage of parent or percentage of daughter, and then tell us this percentage, which then allows us to calculate a couple of things. So let's look at a couple of quick, simple examples. This one doesn't involve any math, but there's the figure. And if I say that a given rock has 25% parent remaining, well, how many half-lives is that? So you'd find 25% parent here on the y-axis, shoot over horizontally till you hit this dark line, go immediately down, and you know that that is 2 half-lives. So after 2 half-lives, a rock is 25% parent, but 75% daughter. And so there's the answer for that question. A second example, and this is the one that is more common. We are asked, how old is this rock? I don't know how many times I've been asked that in my life. And I, as a paleontologist, answered this with a geological relative age term. That's Pleistocene, that's Carboniferous, that's Cretaceous. But if I want to get an absolute age date, this is done from an igneous geologist measuring the percentage of parent. So 25% of the parent remains. We know from the previous example that that is 2 half-lives. And so the isotope we are measuring, we know, has a half-life of 250 million years. So the time from this 0 to the 1, that is 250 million years. But we know that we've taken up another whole half-life here. So it's going to be 250 times 2 half-lives. So the age of this rock is 500 million years old. It can be a lot more complex than this, but this is the simplest algebraic example of how this is done. And on the exam, you'll at least have 1 or 2 of these type things. You can use a calculator, but generally I have these things end in 2s or 5s or 0s for easy multiplying, easy dividing. All right, what do you need to know for the exam? Well, you need to know a few of those relative terms, and you need to know a few of those absolute terms. So first of all, as I said before, the time that the dinosaurs lived on planet Earth, we call that the Mesozoic. It consists of 3 smaller time segments, the Triassic, the Jurassic, and the Cretaceous. You need to know those 4 words. Besides knowing those 4 terms, you also need to know which one's older, which one's younger. And we'll get to that picture in just a minute. And I also want you to know the numerical ages or numerical dates for this thing. So here's what you need to know. Here's a section of the geologic time scale. The oldest stuff would trail off below this diagram, anything younger here. And you see on the extreme left, there's the Mesozoic era. And then notice it's this whole green stretch. It stretches from here to there. And then that encompasses 3 parts: the Triassic, and then younger than that, the Jurassic, and then youngest still, the Cretaceous. All 3 of these geologic periods have dinosaurs in them. We're going to learn later that the oldest dinosaurs, the very first ones, pop up somewhere here in the middle of the Triassic. The Jurassic is their heyday, of course, and that's why the book and the movies and all those things are named after it. And then they live through the Cretaceous, and then at the top of this line where the green ends, that is the end or the ultimate extinction of all of our large dinosaurs. How do we do this or mark this numerically? The start of the Mesozoic era, you need to know this number, 245 million years old. The end of the Mesozoic era, 65 million years old. Those are the terms you need to know. You want to know more? You're interested in this type of thing? Well, your textbook has a pretty good introduction, as I said, that's chapter 3, but I also teach a course, Geology 204, every semester that goes into it in a little more detail for you and maybe leads you down the trail to ultimately doing something like this in life.